Next up, I would like to give an example of this pathfinding problem that is probably the most common example that ends up happening in a robotics class like this, and that is maze solving. Now, that's not going to help us for our spaceships, but there's a good chance that solving a maze is going to be the next gazebo assignment, which is going to come up, so this may be practically useful. So maze solving. We have some set of walls, or obstacles. Maze solving and just planning a path through arbitrary obstacles ends up being approximately the same problem. So we start off with a robot, and I'm just going to make the robot be an arrow for simplicity. And the robot is in some sort of maze. And we want to find the way out. And so in order to find the way out, we need to search the possible space of motions that we can take. But if we think about this in terms of how fast we spin the wheels and like at what angle do we turn the robot, that's not necessarily going to give us a simple way to solve this problem. So it's useful to sort of abstract away a little bit from the direct controls and just ask the question of sort of which direction do we want to go at which point on the map, and when do we want to turn. And so we can see here pretty clearly that the path that we want is going to be to go this way. And that gets us out the top of this maze, and we can see that just by looking at it as humans. But the robot is going to have some sort of sensors, maybe the LiDAR from, well, alright, we have two separate problems. We could give the robot this maze in some format and then tell it to make its way out, or we could not give the robot the maze. Let's first talk about the problem where we do give the robot the maze and save the problem where the robot needs to find its own way out for maybe next week's lecture, maybe the week after that's lecture. So we'll assume we're giving it at least this map. But then we're going to have to take this map and we're going to have to reduce it in some way so that we can treat it as a graph and do graph search. And so the simplest reduction here is going to be to figure out where the possible turns are. So we have, here the robot can sort of only go forward, but then there's a place where we could turn. Here's a place where we could turn. That's a place where we can't really turn, but it's a place we can go. Here's a place where we can go. Here's a place where we can go. And if we follow this plan, we will reduce this maze into a graph where the edges are sort of straight hallways where we don't have any choices, and the nodes or the vertexes are the places where we have choices to make, where there are multiple connected hallways, and we have to pick where we're going, or sort of the dead ends in the hallways are also going to be nodes, because that's a place where we can get to as a result of having made a decision somewhere else. And so this is, again, we have a sort of continuous space here where this robot could be sort of in any position at any angle, but for the purpose of planning a path through the maze, all we need is this graph of sort of the relevant places where we can go. It's not useful to differentiate between like this position and this position, because topographically on the map in the maze, this position and this position aren't different. In both cases, we're going to have to drive that way until we get to this turn, and we have to go that way to get out of the maze. So, sort of two problems here. One is, how do we reduce a map to the graph? And we don't have to solve that problem right now, because we're not actually trying to drive robots through mazes. But what I want to talk about is the second problem, which is how, once we have a graph, how do we find the path through that graph to get to our destination? And the sort of obvious answer is that we just recursively try every path. We do something like depth first search. So the robot starts here, And it has one choice, which is to drive forward to that corner. And so, of course, we're going to see what happens if we do that. We're not going to see what happens by driving the robot. We're going to see what happens by searching through this graph data structure until we get to our destination. And I guess our destination is going to be this vertex up here. We're missing some vertexes that I didn't draw in, but I'm sure you can see where I'm going with this. So at this point, we still don't actually have any choices. There's just one place to go. And if we wanted to optimize the graph, we could sort of optimize out this vertex. But in order to be able to map back location, or in order to be able to convert between locations on our graph and locations on the map, it frequently makes sense to leave in some of these trivial vertexes, which describe relevant places on the map for the visualization, but don't really describe relevant places in the search space. So obviously when we get here, the only thing we can do is go here. And once we go there, we have two choices. We can, we're going this way, so we can either turn this way down this, what we can see as a dead end, or we turn this way and go down the hallway some more. And in depth first search, we pick one and try it. So if we pick this one, we'll go there. And then from here, we only have one option, which is to go back the way we came. Now, if we think about this a little bit more, when we drove from here to here, we actually had two options. We could go back the way we came, or we could continue onwards. And so obviously we want to optimize our situation by not sort of retracing our steps. We know that going back to somewhere that we went previously in this particular problem doesn't help us. And so maybe we want to keep a list of the vertices that we've already visited. Maybe the vertices are identified by numbers in our data structure, but we'll keep track of where we've already gone and not go there again. Once we've gone there, we don't need to go back. And then we can use other optimization strategies like dynamic programming or memoization to do even better. But that sounds like optimization to me, and really what I want to focus on in this class is more how to get a solution rather than how to optimize algorithms. Optimizing algorithms is fun, and you sometimes need to do that, and you sometimes need to go look up how to do that. But in order to get start going in the right direction for how to solve the problem, you don't need to optimize. You just need to have something that works, and then when it runs too slow, then you need to optimize. So we're just going to keep track of where we've been, and logically that's kind of like leaving a track of breadcrumbs behind you. If you know the Hansel and Gretel fairy tale, they were going through the woods and they leave a trail of breadcrumbs behind them so that they could retrace their steps. And it turns out that using actual breadcrumbs is a bad idea because birds eat them and then you can't find where you're going. But using logical breadcrumbs where we like drop like pins on our virtual map so we can see where we've been is a really good way to avoid retracing your steps, because if you go somewhere and look and find a pin, you know that you've been there already. In any case, we'll keep searching, and eventually in a graph this small we'll find where we're going. But in a graph in general, especially if we've taken some large complicated continuous space and reduced it to a discrete graph with many edges and vertices, we end up getting into situations where we have a relatively complicated, a relatively high computational complexity algorithm here. And so maybe you want to optimize more. And in sort of the worst case, this sort of graph search in general, is always going to be something that's going to take exponential time. In specific cases, you can get it down to n squared time, or you'd like to be able to do everything in the world in linear time, but it is possible that you need to do some optimizations. But our basic strategy is just going to be searching the graph by searching it. Maybe we decide that for the kind of graph that we have, depth first search is likely to get us off in the wrong direction, and so we want to do breadth first search. So the idea with breadth first search is that when we get to a node like this one, we're first going to search one direction by one step, and then we search the other direction by one step before searching the first direction by two steps. And that'll guarantee that we find the shortest path if we do a breadth first search, because we will find the path to the destination before we consider any paths that are longer than the path to the destination, which is great until we get into situations where we wanted to find the shortest path in distance rather than a number of graph nodes. You can see here the distance between this node and this node is a much longer distance in distance than the distance between that node and that node. And so if we're doing a breadth first search to find shortest path, we're not going to get, that's a train. live next to a train track. It's spectacular. So yeah, shortest distance in number of edges traversed is not necessarily the same thing as shortest distance in distance traversed, is not necessarily the same thing as shortest distance in amount of fuel consumed. And so the next sort of complication on here is that we want to add weights to the edges. So maybe this is going to be distance 2, this is distance 1, this is distance 1, this is distance 2, this is distance 1, this is going to be distance 3, 1, 3. And then we can try to come up with algorithms that do, that find us a path from the start to a destination that is the shortest in, or that optimizes for the minimum weight of edges traversed. And to do that, you get into famous algorithms like Dijkstra's algorithm or Bellman-Ford, or common in robotics or pathfinding or game AI, you have an algorithm called A*. And those are all algorithms that I recommend looking up just to skim to get some ideas. But we don't need to be able to properly solve this particular problem yet. So I'm going to take a break on this video and then come back a second, and we'll talk about a simplified version of the pathing problem that we actually have for the upcoming homework.